So for today, class will be discussing a new topic, so under a new module, which is now about heat exchangers. So this will be applying the concept of heat transfer that was fully covered already, including the three modes. So we have conduction, we have convection, considering both forced and natural convection, and we have radiation. Okay, so for today, we'll have heat exchanger. So feel free to interrupt me or write something in the chat box should you have any concern as we go along. So let's first go into the different types of heat exchangers and how are the fluids in these heat exchangers contacted, or if there's no direct contact, then how is the direction of flow specifically. So one of the simplest and the cheapest type of heat exchanger is the two concentric pipe arrangement. So concentric in the sense that they have a common center. So several units can be connected in series in this case to extend the capacity of heat transfer. So if we will have a very short length of tube, then we will have a limited amount of heat transferred. So if we're going to connect several concentric tubes in series, then we extend the heat capacity. So I'd like to show to you the manner in which the fluids in these two concentric tubes are being contacted. So on the top part, you can see that you have a counter current flow heat exchanger. So your heating fluid is in the annular space in between the two concentric tubes, and your fluid to be heated flows on the inner tube. So that's the one in blue. Okay, so in this case, they are facing each other. I'm referring to the direction of flow, so we say it's counter current. Now, if it's concurrent or co-current, so we have this one. So they both enter on one side and leave on the other side together. But nonetheless, still the same. Your heating fluid, or in this case, your cooling fluid, is if it's a process of cooling, flows on the annular space in between the two tubes. The fluid to be cooled or heated is flowing on the inner tube. So this is your double pipe heat exchanger. Now, in your book, so this is how it's represented. So your double pipe heat exchanger could be represented in this form in your book. We have one pipe in here, and the fluid that is flowing in this pipe, the inner pipe is the tube side fluid, and the fluid that is flowing on the annular space in between is the shell side fluid. Okay, so in color, this is the one that I'm referring to. So this is a double pipe heat exchanger in counter current fashion. So counter current shot. There's a chat here. Okay, so just for the attendance. So this is the way it's represented in majority of the reference books that you have. Now, a shell and tube on the other hand, so this one is double pipe, okay? Double pipe. What about the shell and the tube? So this is the one actually I used as an example in the topic of heat transfer by convection. So we have a shell and tube exchanger this time, which consists of a bundle of tubes enclosed in a cylindrical shell. So you have one shell housing a bundle of tubes. So the ends of the tubes are fitted into tube sheets, which separate the shell side and the tube side fluids. So the ends of the tubes are fitted into what we call tube sheets. Now, baffles are provided in the case of the shell and tube arrangement to direct or to guide the fluid flow, and at the same time, an added support for your bundle of tubes inside the shell. So this is how a shell and tube heat exchanger looks like. Okay, so what you have here specifically is a two-pass shell and tube heat exchanger. So you have one bundle of tube in here and another bundle of tube in here. So they are inside this particular shell, acting as its house. And you see these lines, these are referred to as the baffles. They guide the flow of the heating medium or the cooling medium, whatever is the purpose of a particular shell and tube heat exchanger. So you have, so the difference of this is in the double pipe, you only have one inner tube and one outer tube in here. You have one outer tube in the form of a shell, and you have tubes inside. Bundle of tubes, referred to as the bundle of tubes. So later on, the manner of configuration of the shell and tube heat exchanger affects greatly the amount of heat that is being transferred to the fluid or from the fluid. So that would be illustrated by a sample problem. So this is just one particular orientation of the shell inside the tube. So one shell, two tube passes in this case. Okay. Something writes on the chat box. Okay. Now we proceed. Now, I have mentioned that you can have a one shell, one tube bundle type. So this one, you have one shell and one tube bundle. On the animated illustration I gave in the previous slide, that one is a one shell, two tube bundles. So you have one bundle on top here and another bundle in here. So the fluid enters in here on the first bundle, that's one pass, and flows on the second bundle, that makes it a two pass shell and tube heat exchanger. So both have one shell, but differs only in the number of sets of tubes inside. Okay. A simple representation of these two modes of these designs of your shell and tube heat exchanger is this. So when you illustrate it in a problem, if you have a one shell, one tube pass type of shell and tube heat exchanger, the blue one in here is referring to your bundle of tubes. The red one in here refers to your shell side fluid. So it could be your heating medium or your cooling medium. This one is your two tube type of shell and tube heat exchanger. You have two sets of tubes. So this is your two sets of tubes. One set for this one, and then this is the other set. This is still your cooling or heating medium or your shell side fluid. Okay, so that's for our shell and tube type of heat exchanger. Now, in here, it's a different thing. So you have one, I'll go back. This is one shell, one tube. This is one shell, two tubes. This one is one shell, four tube, two shells rather, two shells, four tube, four tube bundle sets. So in one shell, you have two tubes, set of tubes, and the other shell, you have another two tubes. So this is also one particular arrangement for a shell and tube heat exchanger. Okay, two shell and two tubes for each shell, making it four tube bundles. Now, this is how we represent it. You need not draw this one in your, when you solve or you present your solution to your problems later on. You may present it in this manner for a two shell, four tube arrangement. Okay, so what are the advantages of the shell and tube exchanger? So the configuration gives a large surface area in a small volume. So it gives good mechanical layout, a good shape for pressure operation. Now, uses well-established fabrication techniques. So meaning this is a well-established design already. Now, can be constructed from a wide range of materials depending on the material to be handled and to the, of course, to the characteristic of the heating or the cooling medium. It's easily clean and it has well-established design. So in the industry, we always use the shell and tube type because they have maximized the allowable surface area for heat transfer. Now we go to the next type. So this is the third type. So we have a gasketed plate heat exchanger consisting of a stack of closed-spaced thin plates clamped together in a frame. So a thin gasket seals the plates round their edges. So in here, you can use alloys, including stainless steel, aluminum, and titanium. So these gasketed plate heat exchangers are what we call as the plate and frame heat exchanger. Okay. Now, this is your plate and frame heat exchangers. Actually, you will see the shell and tube type and this plate and frame type of heat exchangers in the industries that you will do your OJT later on. So it's common in here in Negros. If you go to a distillery, if you go to a sugar central, you will have these particular types of heat exchangers. If you go to Asian alcohol and during your OJT, there could be a time wherein they're doing the cleanup of the equipments. You will see how this is being dismantled and how the plates look like. Okay, so you're really going to see the actual equipments. So the fluids to be heated are passing through the plates and they are held together by a frame. So they are put into one frame, several plates stacked one on top or beside another. Okay. Now, what are the advantages of using the plate and frame heat exchanger? So plates are attractive when material costs are high. So when material costs are high, this one is cheaper than the shell and tube type because in here you simply have to stack plates. Okay, plate heat exchangers are easier even to maintain because they are plain in shape. So not so much with the tubes in which there's a need for you to probably clean the tube inside by boiling acids on it, especially if they're already fouling that is occurring inside and even outside your tube. So that's the main problem with tube types of heat exchangers. Now, for plate and frame heat exchanger, we have low approach temperatures, so even as low as 1 degree. So your fluid as near to freezing temperature, in the case of water, for 1 degree Celsius, can be introduced into this particular heat exchanger. Other heat exchangers needs what we call preheater for your fluid to enter your particular exchanger in a desired temperature or at a desired temperature. So for in the case of the shell and tube, it has to be 5 to 10 degrees Celsius. Meaning if your fluid is as low as this in temperature, you need to preheat it first before you can introduce to a shell and tube heat exchanger. Now, plate heat exchanger are more flexible and they are easy to add and they're easy to extend because you can simply add plates on your frame. So of course, you just simply need to adjust the dimension of your frame. Now, plate exchangers also are more suitable, take note, for highly viscous material. Highly viscous materials are not oftentimes processed using the tube because they easily corrode the tube. So in the case of the plate heat exchangers, they are really suitable for this type of material. Now, there is this temperature correction factor, F sub T, which you will encounter later when you do the actual design of the heat exchanger. In here, for the plate and frame, they will normally be higher than plate heat exchangers compared to other exchangers, the temperature correction factor. In the problem that will be given to you in a little while, we have a temperature correction factor for shell and tube type of heat exchanger. And expect that if your particular design for a shell and tube is replicated to a plate and frame, meaning not in terms of the physical design because they're really very different, but in terms of the required temperature of the fluid as it leaves the exchanger or the required temperature of the fluid as it is to be processed by the heat exchanger. So if you're going to compare these two designs, having the same desired outlet temperature and having design inlet temperature for the fluid, your plate and frame heat exchanger is expected to have a temperature factor which is higher than that of the shell and tube. Okay. Now, fouling tends to be significantly less in this particular exchanger. So I have already mentioned that. by the fact that you have plates only and they are not circular in nature, so foulings tend to be very negligible in these types of heat exchanger. Although klase may ara man siya nga disadvantage because they use gaskets for these types of heat exchangers, then maintaining these gaskets also is something to be considered. Okay, so disadvantage. So a plate is not a good shape to resist pressure. So it's a given. And plate heat exchangers are not suitable for pressures greater than 30 bar. Okay, the selection of a suitable gasket is critical. So I've mentioned this a while ago. While you need to select a particular gasket for your plate and frame heat exchanger that is suitable for the material that it's going to heat or the material that is going to be processed on it, it also takes time for it to be taken and replaced during maintenance, this particular gasket. So this is a consumable. Okay. Now, the maximum operating temperature for this type of heat exchanger is limited only to 250 degrees Celsius due to the performance, again, of the gasket material. So, your limitation here is more on the gasket material that is being used. But as to fouling, its advantage really is its fouling is really negligible. It's okay for in happening here in this type of plate and frame heat exchanger. Now, if we have what we call plate and frame, we also have what we call plate fin heat exchangers. So plate fin exchangers consist essentially of plates. So it has also plates, but this time these plates are separated by what we call corrugated sheets. Corrugated sheets, I think you know what corrugated sheets is. Comparable to our, shall we say, the sheets that we are used in our roofs, which forms the fins. They are made up in a block and are often referred to as, so another name for these plate fin heat exchangers are matrix exchangers. They are usually constructed of aluminum and joined and sealed by bracings. So they are joined and sealed by bracing. So you could see that this is your plate fin heat exchanger types. So you actually have still the plates stacked on one on top of another or side by side, but in between these plates you have the presence of the corrugated sheets. So you have, in this case, you have the cross flow pattern of actually it's not contact, indirect contact of your fluids. So this could be your heating medium because it's red, so it must be at a higher temperature compared to this blue. So it's cross flow pattern, but this one is counter flow. Now, it's seldom class that you will encounter a co-current or a concurrent type of flow for heat exchangers. If you recall our discussion then on the simple, I think I only gave one sample problem, which uses the delta T log mean temperature for the double pipe heat exchanger. And I asked you to do the second of, if I did not ask you to do, I simply gave you the value of the amount of heat transferred if the orientation of the direction of the fluids as they transfer heat one onto another is, one is counter current and one is co-current. You will learn, and as discussed by John Cook, discussed that counter-current flow will always have a greater amount of heat transfer than co-current flow. That is why in the industry, they seldom have this co-current flow for your fluids, wherein heat transfer is going to occur. So it could be counter flow or cross flow in this case. So I have recalled it in our discussion then. Now, what about this plain fin heat exchanger? So they are now finding wider application in the chemical process industries where large surface area compact exchangers are required. So their compact size and low weight have led to some use in offshore applications. So take note of the specific special applications of each of the types of heat exchangers that will be discussed in this slide. So brazed aluminum construction is limited to pressures up to 60 bar and temperatures up to 150 degrees Celsius in this case of the plate fin heat exchanger. So this is even more limiting than the previous one, which can have at most 250 degrees Celsius, the plate and frame. So this one can only carry up to 150. The units cannot be mechanically cleaned, so their use is restricted to clean, process, and service streams. So as much as possible, the fluid need not be viscous because your fluids have to be in the first place clean. All the service streams that it has to process has to be clean. Now, so we have double, we have shell and tube, we have plate frame, we have plate fin. This is the fifth, and we have the spiral heat exchangers. Actually, it's like your plate frame which rolled, which you did the rolling of the plates. So a spiral heat exchanger can be considered as a plate heat exchanger in which the plates are formed into spirals. So the fluids flow through the channels formed between the plates. So your fluids flow through the channels formed between the plates. So it's just like in our language, daw ginroll mo lang ang imo nga nakastack nga plates. Then that would be your spiral heat exchanger. And this is your spiral heat exchanger. So how it looks like. So your fluids flow on the space, the annular space in between your stack plates. Okay, it's being introduced in here. So you have here cold fluid, and this one is your hot fluid leaving your exchanger already. So this is your spiral heat exchanger. So let's look into its specific application. What makes it so special? Why create this particular heat exchanger if the other designs will suffice already? So ang question nga kadamo, ganyan type kung pwede man lang po ang iba nga na-discuss na. So let's look into it. So for a given duty, the pressure drop over a spiral heat exchanger usually be lower than that for the equivalent shell and tube exchanger. If you want to minimize pressure drop, your design should be this one. Spiral heat exchangers give true countercurrent flow, so meaning it maximizes the amount of heat to be transferred and can be used where the temperature correction factor for your shell and tube heat exchanger would be too low. If you recall, I mentioned a while ago that the temperature correction factor for a plate and frame heat exchanger is higher than the shell and tube. So meaning the temperature correction factor for the shell and tube will, as expected, would be low. If you want to address this low FT, which will result actually to lesser amount of heat transferred, later you will see in the formula, then you convert your design to this type. If you want to address the very low temperature correction factor in your shell and tube. But oftentimes, class in the industry, since this is well established already, the shell and tube, amo maging siya ang ginagamit. Because they are easily cleaned, referring to spiral heat exchangers, and the turbulence in the channels is high, spiral heat exchangers can be used for very dirty processed fluids and slurries. So there was no mention about a special type of heat exchanger that can process these types of fluids. So the plate and fin is even very limiting because it can only process clean fluids. So this one is a complete opposite. It can process very dirty processed fluids and even slurries. Now, so the sixth, so we have the sixth type of heat exchanger, the scraped surface heat exchanger. I think its name already implies what's the special design for it. So heat transfer to and from, take note, its special application, viscous liquids, especially food products and other heat-sensitive liquids is often accomplished in scraped surface heat exchangers. So they are often used class in the food industry. So typically they are double pipe heat exchangers with a fairly large central tube. So the double pipe lang siya nga dako ang imo central tube, 100 to 300 mm in diameter, jacketed with steam or cooling liquid. And since you have the presence of this viscous liquid, or it is processing viscous liquid, your central tube has what we call a scraper. Okay, this is the design for the scrape surface heat exchanger. Okay, this is your central tube that is being referred to. It's large compared to the one that we had in the double pipe or concentric heat exchanger, and this is your outer tube. To ensure that no material remains deposited on the shell side of the outer tube, you have these scrapers. It cannot really be avoided if you're processing or if your exchanger is processing viscous material. So if exposed to very high temperature, or if the temperature is increased, this particular viscous material will tend to have some solids on it or even solidify if the increase is elevated in temperature, I mean. So these particular scrapers will ensure that no solids will remain clinging to the shell side, to this shell side in here. As to its cross-section, it will look something like this. This is your central tube. This is your tube wall. This is where your process fluid is. And this is your scraper that ensures that no solid remains on the surface in here. So siya ang nag-scrape. Okay? Now, since you have here surface fluid, then this particular scrape surface heat exchanger could be the one that is mentioned in the previous slide as the one that has a jacket. So in the jacket, you have a fluid. So whatever the purpose of that fluid may be, it could be for heating or it could be for cooling. But take note, the special application of this scrape surface heat exchanger is for viscous materials, specifically in the food industry. So it's always stainless steel. Okay, now what are the design considerations? So we have already gone through the different types, the common types of heat exchanger designs. And what are the design specification, or specifically what are the formulas that you are to utilize when you encounter problems concerning the heat exchanger? You have already determined the loop-mean temperature difference then when we solve a problem regarding two concentric tubes, heat exchanger. So you have an inner tube and you have an outer tube. So in that case, we simply made use directly we made use of the delta T lube mean in determining the amount or the rate of heat that is being transferred. Now, in the case of the lube mean temperature difference here, and the temperature correction factor, and the case about the temperature correction factor, when are you going to use this? Because if the original equation would be applicable or would be enough to consider all design considerations, the one that has a delta T lube mean, why have this formula for the temperature correction factor? The temperature correction factor class is used when you have a shell and tube type of heat exchanger. If you have a double pipe, it's okay if you're simply going to use the formula UA delta T lube mean without having to consider the temperature correction factor. But if you have a shell and tube type wherein, as shown to you, we can have three possible orientation: one tube, one shell, one tube, one shell, two tubes, two shell, four tubes. Even in Paris, there is even three shell, six tubes. Okay, so I'm not sure about on the 9th edition how many orientations is added there. So you have to consider what we call as the temperature correction factor. And what is that? We will learn that later in the use of the diagrams and graphs that I will show to you. Your formula for Q will still be very much guided by this general formula, driving force over resistance. If it's expressed in terms of the overall heat transfer coefficient U, it's like this. If you use the inner part of the tube characteristics or the inner fluid as the basis for determining the amount of heat transferred, so this will be your formula. If it's the outer part of the tube or the outer fluid, this would be our formula. All three will be equal because when you speak of heat transfer, what is the amount of heat transferred from one fluid will be the same amount of heat that is received by another. So we neglect any losses unless the problem specifies that there's a corresponding heat loss. Okay. Now our resistance, as you can see in here, even if this one is not written, our resistance is actually in here is 1 over UA. 1 over UA. That is why the UA is already written in the form of a numerator multiplied to the delta T in here. So your resistance could be this, or could be this. Now, if we are to consider both conductive, so for the wall, and convective heat transfer, so this is our complete, or this is the sum of the resistances that we are to account for our amount of heat transfer. So this would be your UI. Your UI is this. Your UO is this. Your UI and UO has to be equal if there are no losses. Now, your delta T lub mean was already given to you in the previous example discussed, and the formula is this one. As to what is the delta T2 and what is the delta T1 depends on the orientation, whether it's countercurrent or concurrent. So anyway, it will be shown to you in a little while what is this delta T1 and delta T2 again. Now, when you are given a shell and tube type of heat exchanger, you don't use the delta T lub mean only in the formula in determining the Q, but rather you use the delta T mean. So what is the delta T mean? It already multiplies to your delta T lub mean the temperature correction factor, okay, the FT. Now, where are you going to get this FT? So we're going to go to the next slide. Okay, so Jelaine, so we will continue. Before we go to the temperature correction factor, so this is our delta T2 if we have a concurrent flow. So parallel flow, delta T2 is the difference between the inlet temperature of the hot and the cold fluid. Delta T1 is the difference between the outlet temperatures of the two, hot and cold fluid. If it's countercurrent, so your delta T1 will be the difference between the inlet temperature of the hot fluid and that of the outlet temperature of the cold fluid. So they are now facing each other, countercurrent. So delta T2 will be the difference between the outlet temperature of the hot fluid to the inlet temperature of the cold fluid. So delta T2 and delta T1 depends on the orientation of the direction of flow rather of your fluid. So this is how it's going to be. This is your co-current or concurrent or parallel, as some other books would refer to it, and this is your countercurrent flow. Now, where is this temperature correction factor? In your handbook class, there are a lot of graphs like this. You can have a 1-2 graph, you can have a 1-4 graph, you can have a 2-4, you can have a 3-6. As I said, I can't really memorize what's now in the current edition. So what you have in this graphs class are 3 values actually. You can get your temperature correction factor for heat exchangers which has this orientation as long as you already know the Y and the Z. So as to what is the Y and the Z, you just have to make use of this formula. So HI, inlet temperature of the hot fluid, HO, outlet temperature of the hot fluid. CO, outlet temperature of the cold fluid, and CI, inlet temperature of the cold fluid. Now, you have 2 different formulas for these two. The Y values you use here on the horizontal axis. Kindly mute yourselves, please. Your Z value for these curves. Okay? Your Z values for this curve. So if your Z value as computed does not really lie on a specific curve in here, you just have to, shall I say, make banta-banta in our language. Approximate, let's say it's a 0.3, so it's somewhere in between 0.2 and 0.4. So you just draw your curve in here. You just follow the shape of the curve. Okay, so if it's like 1.2, so it's between, or 1.25, it's between this one and 1.5. Okay, that way you can get the temperature correction factor. Okay, so this is for your 1214. I took this from John please. This is for your 24. Okay, please mute yourself. Please, maybe not in his table. Let me check. Jelaine, can you please mute your mic, mute your microphone? Maybe she's not there. Okay, so this is for a 2-4 exchanger. Okay. Now, this is one method you determine the amount of heat transferred. So it will be used later on in a particular formula. You will account for the temperature correction factor from these tables here, or the appropriate, not tables class, I keep saying tables, graphs. You can use the appropriate graph in your chemical engineer's handbook, depending on the design that is given to you in the problem. There's another method that we use in determining the amount of heat transferred in a particular heat exchanger, and we call that the heat exchanger effectiveness. Now, you may think, okay naman to siya, miss, na-consider ta naman ang design sang shell and tube. So we already had the temperature correction factor. There are problems, class, in which the outlet temperature of the fluids are not given. So the lug mean temperature difference will only work if you have all 4 temperatures complete. Kompleto na siya dapat ang 4. So if it's not complete, if what is known only are the 2 inlet temperatures, the lug mean temperature difference method will not work. So then you should have an alternative method to use. Now, especially some unit of problem on heat exchanger design does not give you the complete 4 temperatures of your fluids. So that's the heat exchanger effectiveness method. Now, what is this effectiveness? So it's the ratio of the actual rate of heat transfer in a given heat exchanger to the maximum possible amount of heat transferred if an infinite heat transfer area were available. What we mean with an infinite heat transfer area available is if in terms of heat transfer area, there's no limitation. Then we can use the heat exchanger effectiveness method. Now, I've mentioned this already. When the outlet temperatures are not given in the problem, you use this particular method. Now, what do you have in this method? Now, in the case of heat exchanger effectiveness method, in this case, I use the orientation of the counter current flow. And you could see in here that you have the CH greater than CC. Now, in the first place, what is the CH and what is the CC? Now, the CH is simply the product of the mass flow rate of the hot fluid and its specific heat, or its heat capacity. CC is for the cold fluid. Now, in this case, in this orientation, most of the time, class, your MC for the hot fluid product is greater than the MC of the cold fluid product. If that is the case, you will use this particular formula in computing for the amount of heat that is being transferred, either from the hot fluid or from the cold fluid. Now, if it's the amount of heat transferred from the hot fluid, of course, your fundamental formula in thermodynamics, MCP delta T. So this is the amount of heat that is being transferred from the hot fluid, the same amount of heat that is being received or absorbed by the cold fluid. So MCPH, MCPC. Now, if the temperatures are not complete, how are you going to compute this then? Let's say, for example, ang ginhatag lang si HI kag si CI. So you cannot complete, you cannot solve any unless you have one outlet temperature. So what if you don't have both outlet temperature? So you cannot go back to this fundamental equation. You need a substitute equation that will only need the inlet temperatures. So that particular equation is the one given here. So you have the C min. So the C minimum is the CC actually, the C sub C, the product of the mass flow rate of the cold fluid and its heat capacity. You have here the difference of the inlet temperatures of the hot and the cold fluid, and this time you have this effectiveness. You need the effectiveness if you don't have any of the outlet temperatures. So this is the formula that you will use, effectiveness if the outlet temperatures are not given. The question is then, where will you get this effectiveness or this epsilon? Now, the effectiveness for counter current flow is given by this formula. Now, if you look closely at the formula class, it needs the overall heat transfer coefficient and the area. If you can get the C min and the C max because the temperatures of the hot and cold fluid are given, and you can get the CP from a particular property table, still you will have a challenge if this two is not given, the U and the A. So how will you find then the epsilon if you are not provided with this one? You will use the number of transfer unit formula. So the number of transfer unit formula, which is equal to UA divided by C min, you can use. At again, class, you see this? May ara man siya gyapon UA. So you have actually a choice whether you use this formula, which is the UA, or you use this particular simplified formula, which also has the UA, but will use a particular graph again. I did not use the table term. So you will use a graph. What is that graph? And by the way, class, this is for the co-current. So we have a different formula for counter current for effectiveness, and we have a different formula for co-current. Okay, so where will you get the epsilon? If let's say, for example, the NTU is given and the UA is not given. So you need to get it from a graph. Okay, and this is the graph that I'm referring to. You have also an equivalent for this in your handbook. Letter A is for counter current flow, heat exchanger. Letter B is for parallel flow, heat exchanger. What you have on the curves for both of these graphs are the ratio of the C min to C maximum. So 0 for the first, 0.2, 0.5, 0.75, and 1. If the particular C min to C max ratio that you have does not fall on any of the specific curves, then you just approximate where that particular value is in terms of the curve. So you just draw your approximate curve for that. Same thing in here. So in here on the horizontal axis, you have the NTU. So if the problem does not give you the UA, then and the problem give you the NTU, then you can use this graph to get the effectiveness. Same thing in here. Because if you're given the UA, you can actually solve right away the effectiveness based on the two long formulas I gave you. But if you find it cumbersome to use that particular formula, you can use this particular graph. Although the formula is still more accurate to use compared to the graph. But this is just an alternative if the UA is not given and the NTU is specified in the problem. So from the two here, from the two graphs, you'll be able to get the effectiveness. Once you have the effectiveness, then you go back to our formula in here. Effectiveness times C minimum times the difference of the inlet and outlet temperatures of your hot and cold fluid, respectively. So when will you use this? When the problem does not give you the outlet temperatures of your fluid. Okay, now I hope I can finish everything so that tomorrow we'll have the sample problems only. Now, in heat exchangers, we cannot really do away with fouling, especially with the use of the tube types of heat exchanger. So what is this fouling? So fouling actually is the deposition of any undesired material on heat transfer surfaces. So fouling may significantly impact the thermal and mechanical performance of your heat exchangers. And it is a dynamic phenomenon. That's the very basic reason why we have regular periodic cleanups in industrial facilities which uses heat exchangers, because the tubes have to be clean. Okay, so fouling increases the overall thermal resistance. So it increases the thermal resistance and lowers the overall heat transfer coefficient of your heat exchangers. So fouling also impedes fluid flow. So aside from lowering the amount of heat to be transferred, it decreases the fluid flow, accelerates corrosion. So isang solids ang metal, and increases pressure drop across your heat exchangers. So with all these disadvantages of the fouling, it has to be addressed also. Or in the design of your heat exchanger, it has to be considered. Okay, so in the case of scaling, so you have here a case of scaling here that is occurring on the outer part of the tube. So you have the appearance of the scale. So this is your bundle of tubes actually. You can have particulate or sediment fouling in this case. The two illustrations I have provided here. So that's also fouling. And you can have corrosion, especially if the fluids that are being processed are toxic. It eats up the metal. And you have here a case of chemical fouling. Okay, the tubes are fouled up by the metals that is being processed on it. So you have these particular solids in here. In here you have this particular chemical fouling on the outer part of your bundle of tubes. Now, this is not much of a problem in our end, but freeze fouling also occurs in the western part of the globe, this one. And biological fouling. So these are living organisms fouling up a particular heat exchanger, or I think this is the outer part of the tube. Now, how are we to address fouling? So fouling tendencies depends on the type of heat exchangers and the fluids process. So during the design stage, certain considerations may help minimize fouling in your process or during your processing of the fluid. If possible, allocate the more fouling fluid to the tube side. So meaning atong dako ang possibility nga i-foul up niya ang tube, dapat ato siya sa inner tube. So it should be on the tube side, not on the shell side fluid. Design for fouling fluid velocity of 5 feet per second on the tube side and 3 feet per second on the shell side. So these are suggested velocity to lessen the effect of fouling, or to decrease the rate of deposition of solids or materials in the inner and outer parts of our tubes. And try to keep the fluid velocity constant. Allow for easy access of cleaning. So your design should consider this. What will happen if there's a need already to clean? Or what will happen if there should be a regular cleanup for your heat exchanger? So there should be easy access for cleaning. Now, in water service, ensure that the tube wall temperature is not too high to create salt deposits or render treatment chemicals ineffective. So, kinahanglan kung tubig ang aton gamiton, ang tube wall temperature, ang sa sulod, meaning sang tube nga temperature should not be too high. Do not throttle water flows in winter time. So, this is not much of our problem here because we don't have winter. But throttling, I think you know what throttling is, when you suddenly decrease the area or constrict the area to increase velocity. Okay, so do not do that in here do not do that. It's not suggested during winter, okay, or in the western part of the globe, which has this particular weather or season rather, this particular season. Okay, now almost done. For heat exchanger fouling, this is what is happening. So you have the scale build up on your inner tube, and you have another scale. There could be also scales on the inner tube, on the inner part of your outer tube. So these are scales. Okay, and the usual heat transfer resistance that we account for in terms of the U only accounts only for the resistance due to thermal conductivity and resistance due to convective heat transfer or due to interface. So this is covered already in our convective heat transfer. If you will have to consider in your design the effect of fouling, there are two added terms in the denominator. This is the fouling on the inner part of the tube, and this is the fouling on the outer part of the tube. This is the heat transfer coefficient due to the inner fouling of the tube. This is the heat transfer coefficient due to the outer fouling of the tube. These three are your standard terms if you don't consider fouling in your heat transfer resistance. Okay, so we will have a problem also on fouling, so you will know how to account for those. Now tomorrow, that's Wednesday, we will discuss the 3 sample problems here. Hopefully I can finish everything. If not, I will just again have a recorded link for the 3rd sample problem if I can only cover the 3. Okay, any question, class? For now, I covered all the concepts. That way I can directly go to sample problems next meeting. Now, the source of this slide, if you notice, if you look at the slides, you could see that I have written Colson and I have John Kuplis and I think McCabe. So it depends. This is actually a slide which consider all 3 sources. What you have in McCabe and what you have in John Kuplis regarding heat exchangers is not really comprehensive. Though, ang gani pang discuss ni John Kuplis sa heat exchanger daw, 3 lang na pages. So, the individual designs are not included there. So, I got the other materials from McCabe and from Colson. So, if you have time, you can also check on Colson because there are a lot of downloadable soft copies of his books, which has different volumes. And you have also heat exchangers in one of the volumes there. Okay. We will see each other tomorrow, Wednesday, same time, 11:30. Yes, 11:30 to 12:30 for the sample problems on this. And I will make sure that I will be able to upload tonight your problem set for heat exchangers that you will process during your dry lab schedule tomorrow as well, because you have a 3-hour dry lab schedule. That's the purpose of that. Again, on Wednesday, you will have your quiz, a 1-hour quiz only. Anyway, short man lang ang problem sa natural convection and radiation. I will stop sharing anything. Do you have any questions? Let me check the attendance. So we're 11 now. Have any questions?
None, Miss.